Nicolas is basically presenting, as I said before, he's a regional technology engagement manager for ICANN and travels the world to do these types of things. So he's great at doing this stuff. And I'm going to turn over both to him and to David. I'll let David start first. So welcome them both, please.
Thanks, Stephen. And good afternoon, everybody. Thanks for joining us today. So the purpose of today's tutorial is going to be to learn how to configure BGP between an ISP's border router and an IXP, and then link that border router to an RPKI validator. And today's validator is the software we're going to be using is Fort. Once we do that, we're going to then perform an attack, and we're going to learn together how to use RPKI's tools to mitigate that attack. After we do that, we're going to talk about anycasting DNS servers and about putting RPKI ROAs in place for the anycast prefixes. Now, all of this is going to be done by you on your laptops using a virtual lab environment that ICANN has set up for you, and you can access simply via any web browser. Throughout the next 2 hours, please don't hesitate to stand up, raise your hand, interrupt us, ask your questions. Ask the questions while it's relevant during the steps. Please don't wait until the end. Let's make this a good conversation. So, to lead today, I'd like to introduce to you my privilege as Nicolas Antoniello, who's ICANN's Senior Manager of Technical Engagement for Latin America and the Caribbean region. And Nicolas is going to walk us through setting up the lab and doing the exercises. Nicolas.
Okay, thanks, David. So it's the sound okay? Yeah, okay. So hello everybody. As David said, my name is Nicolas Antoniello. I'm based in Montevideo in Uruguay. That is the far south. Actually, Montevideo, this is a kind of general information that nobody cares about it, but it's interesting. It's one of the most southern capital cities in the world. So I think it's Montevideo and the capital city of New Zealand. There's no capital city more to the south than those two. So we are, kind of far from here, but very happy to be here with you and to go with you through this session. So let me first put up a presentation. It's a slide, because for us to be able to go through this lab, you will need to open your computers. So please, all of you, whether you are a technician or not, take out your computer, put it on the table, and what you will need is to open a browser, and from there we can take from there with the lab. So I'm going to share one of the most important things for today. It's to share with you the way to access the way you're going to be accessing the lab. Okay, let me just put this presentation up. Okay, and let me share it. This is it. So once you have your laptop open, please go to that URL, HTTPS. It could be HTTP, and it will redirect you to HTTPS, nano.te-labs.training. Once you are there, it's going to ask for a username and a password. The username is nano, all lowercase, and the password is that thing, Erin uppercase, ICANN lowercase, 2024, nano uppercase, okay? That should be all, and that should be the only instance today that you're going to be needing to write the password, okay? Once you go through that password check, you're going to be entering the lab. Once you enter the lab, once you go to the next screen, just wait there, okay? We are going to tell some general information, things you should know before starting with the lab, okay? First of all, this is a lab that it's running, that we developed at our team at ICANN, that is running on a cloud server somewhere. I think it's AWS services running somewhere in Virginia, in North Virginia, in a data center in the US. So we have a virtual server there with all the virtual machines created into that server. There are containers that will run all the infrastructure that you will be configuring today. So we will have routers, we will have clients connected to networks connected to those routers, and that's all what we are going to use during the practice. For the router stuff, we use a software router called FRR. I'm sure most of you should know about it. You may know about Quagga, which was like, I think it's the older name for what then became FRR. But it's a well-known software router with a CLI very, very similar on purpose to the Cisco CLI. Okay, so it makes it easier for anyone, at least knowing how to work with Cisco CLI, to go with the FRR CLI. Okay. If you are not a technician and you say, what am I doing here? Just please open your laptop and try to go to this lab. This lab will be step-by-step guided, so you can do it even if you're not a technician. Even if you never get into a router, even if you never configure a router, this is your opportunity to start playing with this and maybe learning and maybe teaching us also something about this, okay? At any time, if you have some question, if you have some comment, if you have some suggestion, recommendation, just raise your hand, go to the mic and ask it. Let's do this like fluent and interactive, so nobody gets bored about this. Another thing, I'm sure there are a lot of experts here with us, probably a lot of people that knows far, far more than we know about this. It's okay for you if you can also go through the lab, because it's very useful for us to get feedback from those experts that know a lot about this. And it's very, very interesting and very good for us to get, okay, how can improve the lab? What would you love to see there in the lab that we haven't done or built into the lab yet? So whether you're an expert or whether you never use a router, please, if you have the opportunity and you have a laptop there, just open it and go through the lab, okay? That's and one last thing is, most of us are probably technicians, and technicians, we love to do stuff before they tell us to do it, especially if we know about it, right? We go ahead and do this and do that. We never hardly read manuals. Who reads the manuals? Only when you are really in trouble, you read a manual, right? And if you put a red button in front of a technician, the technician will trigger the button. So never put a bomb button in front of a technician, because he will blow the bomb. Yeah, we always, and if it's red, it's like, oh my God, there's a reason they put this in front of me. Baf! Okay, so try to moderate your technician nature and go with the crowd, right? Let's go everybody together, step by step. And again, any comment, any improvement suggestion, any question, you're very welcome to do it. Okay, so up to this point, and if at any time anyone gets lost or anyone sees that it's not working or it's not being able to do, just raise your hand and one of us will go and help you going through that, okay? So at this time, I'm going to ask you a question, and the question is there anyone here that wasn't able to get to the next screen? I mean, to get to that URL, put the username, put the password, and get into the lab? If you did that correct, you should be now facing, let me put it here, you should be facing this, okay? A very bad-looking web page with that says "Welcome to nano.tlabs.training lab." Then there's a first sentence there that says "Lab Guide," and it has an open. So please click on the open link, right? That should open a new screen on your browser with what is going to be the guide that we are going to be following along the lab. So you don't have to make an effort and check the screen. You will have it in your own screen, and you can go back and forward as much as you want, and you can even replicate the lab after this if you want. We are going to left the lab up and running until the end of the week. So you will have all the week to play with the lab and to do stuff with that. Please just don't break everything, okay? If you can. If you want to break everything, well. Okay. So what else? Okay, let me go back to this screen. So now what I'm gonna do is I'm gonna assign each of you, as we are not a very big crowd. I'm gonna like point at each of you and assign a group number, right? Just please write it down or write it in your memory, because I'm not gonna remember the number, and I'm not gonna say it again because I'm gonna forget as soon as I tell you the number, okay? And that's the number you will use for the rest of the tutorial, okay? So you're gonna be group number 3. Group number 1 and 2, I was the one that built the lab, so I keep it them for me. So you're group number 3, group number 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Is there anyone without? Okay, is there anyone without a group number? No? Okay. Great. So now what you're gonna do is you're gonna find your group number there and connect to your designated lab environment, okay? I'm gonna connect to mine, which is group number 1, which I have it here. Okay, when you click on your designated group, you should see this screen again. We will open a new screen with this, and you should check there that says group and your group number, okay? As I'm group 1, there says group 1. For if you are group 20, it should say GRP 20 at the top of the screen. If it says so, you're okay, okay? If you get into someone else's group, just close the window, go back to the web page and open the correct group, okay? So, anyone needs more time to get to this web page? Okay, I guess everybody's there. Well, this is the network, the topology of the network each of you have already, okay? So that's a network like this for each group created. That network has, it's not really all of this, it's only the router that says RTRX, okay? And then the 3 networks, the black one, the violet one, and the green one that are connected to that router. Those 3 are the networks that you have, plus the RTRX router, plus the CLI, the client device that is connected to the router. So you will have access to the router and you will have access to the client. The rest of the devices that are connected to the red network are kind of the backbone of the lab. So we also have already, oh, that's disable, right? This is green. Okay. So this is the router that you will be having access to. This is the client you will be having access to. All of this is the infrastructure that each of you will now have access to. And this network here, it's like, as I was saying, the backbone of the lab, with a router that we call iBorder RTR, which will be acting as a IXP central router. Each of your routers will be acting as an ISP router, and that you're willing to connect to the IXP to exchange routes. So we are going to be, as David said earlier, we're going to be setting up BGP sessions between these routers. You are going to be setting up BGP sessions between these routers and the central router. That's one of the first things we are going to do, okay? There are 2 RPKI validators already up and running. These RPKI validators are running validator software called Ford, which is one of the softwares that you can use for RPKI validators. There's another one called Routinator that you can also use, and there are 2 or 3 more, which are the most famous and the most used ones. You can choose if you're going to kind of replicate this and you want to run an RPKI validator. You can choose Ford, Routinator, or whatever you want. Okay. These are already up and running. We're going to talk a little bit about those and going through very fast through the configuration of that. There's a tutorial that's already built into the platform that I will be pointing you, and you will be having a link to go to that tutorial that tells you basically how to install from scratch and configure. You actually have to compile it, a Ford validator, in case you want to do that in a different environment, okay, at home or at work or wherever you want to do it, okay. So after we have these routers connected to the central router with IPv4 and IPv6 BGP sessions, we are going to set up a router connection to each of the RPKI servers, okay? And we are going to start getting in the router the routes from the central router, from the ISP central router, and we are going to be starting getting the RPKI validation information from the RPKI servers. And we're going to go through the BGP table and see how that changes the way that the BGP table is shown, like how are the networks shown and how the validation state for each of those networks is shown in the BGP table. Then we are going to perform an attack. We are going to discuss about a little what kind of attack that is. And you're going to be able to check that something is going wrong or abnormal. And then we are going to try to mitigate the attack using routing policies that take into consideration the validation state of each network, okay? And that's going to be the end of the practice. And then we are going to have a little discussion about how to take it from there to Anycast DNS servers with RPKI in place, okay? Well, let's start. So first, so remain there for a moment. I'm going back to the lab guide. We have this this is public. You can access it from anywhere. It's on GitHub. This is actually some practice that we developed for the LACNO community, the Latin America and the Caribbean Network Operations Group community. And we've been doing like this for a while, but we very welcome any improvement suggestion, as I was telling you earlier. So you can access this from now on from wherever you want. Okay. First thing we are going to do is we are going to talk a little bit about the RPKI. So we go back, we go down, and this is the first part of the guide, right? Verifying Ford RPKI validator configuration. So I told you that the RPKI validators are already up and running, yeah? Ford, it's one of the flavors of RPKI validators that you can use, and it has, of course, it has its own configuration files and everything. I'm gonna talk a little bit about, this is a kind of example of configuration. This is actually the configuration file from the actual validators that are up and running. This has a lot of stuff in the configuration. We are not going in this tutorial through how to configure, how to set up and configure an RPKI validator. We will need like a whole day to go through all of this. But some of the most important stuff that it's in here, this is for Ford, right? This applies only for Ford. If you are doing Routinator or any other validator, of course it will change the configuration file, but the ideas are mainly the same. Only you will find it in different places and with different syntaxes, okay? So the TIL, this is the directory, the local directory where you are running in the server where you're running the Ford validator, where the validator is going to store the 5 TILs that it gets from the 5 different RIRs, right? This is where the local repository will be located. So after it processes everything and generates a single file, generates a single file with all the prefixes for the whole internet routing table, IPv6 and IPv4, with all the ROAs that are created, and it places that file here in the local repository directory you specified, okay? And that's the information routers will be pulling from the RPKI validator, okay? Then you have some more information, and this, I want to just stop a little while here when it says some of the server configuration and specification. It says interval, and then it says validation, and there's a number, refresh, and there's a number, retry, there's a number, expire, there's a number. Those are the timers in seconds where you specify how often you will trigger a validation cycle for the validator. Each time a validation cycle is triggered from the validator will get all the RPKI related information from all 5 RIRs, will process it, and will update the local repository, okay? So if you put 1 second here, that's too often, right? You are triggering each 1 second, it's not gonna be even able to do that, okay? This is, 900 seconds. It's something more reasonable. It may still be too often because the RPKI information from the RIRs doesn't change that much. And you can say, okay, but how about if someone creates a new ROA and I wanted that to be reflected in my RPKI validator? Well, you of course you will have to wait for in the worst case for the next validation cycle, right? Until you get there, your validator won't know anything about those new ROAs that were created. After the next validation cycle completes, you will have those new ROAs, those expired ROAs, those whatever changes in the RIR's database. It will be reflected in your local repository, okay? And then you have like the refresh, the retry, and the expire. Those timers had to do with what happens if your validator cannot contact the repositories, how many times it will attempt to retry, and after a certain period of time that you specify here, basically at the expire, your validator will stop trying to fetch the information. Okay. You can play with these numbers. These numbers represented here are reasonable numbers. So if you put these numbers into a real configuration, it will work. Then you have to go and do some research, and every situation is different. So you may want to lower a little bit these ones, or you may want to put these numbers higher, so it doesn't go that much frequent. Okay, but that's up to each case, and you have to do a little research and give it a try and experiment with this for a while to get to your perfect numbers. Okay. That's enough for RPKI configuration file. Okay. If we go down in the lab guide, let's go for the first task. Let me go down a little bit to here when it says viewing errorways via an RTR client. This must be executed in the CLI device. So what are we going to do now? We are not yet going into the router and start configuring the router. What we are going to do is we already have the 2 validators up and running. They've been actually running for 2 days now. So they are going to many validation cycles, okay? So they have the information about all the prefixes in the internet, IPv6, IPv4, that already have a ROA in place. That information is in the RPKI validators local repository. And what we're going to do now is, let's go to you go to your network diagram and just go over the CLI with the mouse and just click on it. It should open a new window, a new browser window, and be patient, in a couple of seconds or so, you should get something like this, okay? Everybody was able to get here? Raise your hand if you are not able to get to this screen. Okay? So this is the clear line. This is the command line. This is an Ubuntu server version. I think it's 2004. Yes, it's rather old. We are porting all of this to Ubuntu 2204 and 2404, which is the latest stable version, but we haven't completed that yet, so we still use the 2004 version. But this is a normal, full functional Ubuntu server, okay? That we are going to use as a client, okay? So what we are going to do now is you will need to change to the root user, because we will have to install a library that I forgot to install during the lab setup. So you are going to be installing stuff. Please, technicians, do not install anything that is not needed for the lab, okay? Yes, you have root access. You can do whatever you want with the server. Please don't do it, at least not during the next 2 hours, okay? Okay, so the command, for those of you that don't know about this, the command you have to execute is sudo space su space minus enter. And it won't ask you for a password. This is no password. And you get to the root prompt, okay? Now you are the god of the route, of the client. You can do whatever you want with the client. What we are going to do is following the lab guide. Let me find the lab guide. Okay, following the lab guide, we are going to execute this this command. You can copy paste from the. So if you are following the guide, you can go and copy paste this command. It says sudo apt install live rtr0. This is a library that it's needed for what we are going to do. Okay, and by the way, I don't know why I put sudo here, because we are now root users, so you can get rid of this and just write apt install and the name of the library, which is librtr0. Okay, so you can just copy paste from the live guide into the client, press enter, and okay. For me, it says 0 upgraded, 0 installed, because I already installed it while I was testing this morning. But for you, it's going to really go and take a couple seconds in order to install all the library, okay? So in the meanwhile, while you install the library, I'm going to tell you what we are going to do. So what we are going to do, we are going to use this software called RTR client. This software kind of simulates or acts as a router and can exchange information with an RPKI server. So this software will pretend it's a router, will connect, we will see how, we'll connect to the RPKI server and will be fetching information from the RPKI server the same way a real router would do, okay? And what we are going to do is we are going to pull the whole RPKI local database from the RPKI server into the client, into a text file. So then we can go through that text file and see what's really in there, okay? Have you all able to install the library? Yes? Anyone have issues installing the library? All right. If you have issues and you can do some part of the lab, please tell, because if you get stuck, you won't be able to continue with the rest of the lab. So, and this is kind of the whole idea today. So, okay, next command. You can copy paste it from here. Okay, this is a lot of copy paste, but we are going to explain each thing we are doing. Okay, so the next command we are going to execute is this. We are going to use the RTR client, as I told you, to fetch the whole local database from the RPKI server. And the command line goes like this: RTI client -e -t CSV. That's the format of the local file you are going to create with information. We want this very well-known comma-separated values text file, -o roas.csv. That's the name of the output file. So we are going to create a CSV file, call it roas.csv. And you have to give the connection type, which RPKI between the router and the RPKI servers uses TCP connections. So you have to specify TCP and the IP of the validator, which for us it's we are going to use the IPv4, which is 164.0.70, which is within the private space assigned to the lab, and the port. If you go back to the part when we show the configuration of the RPKI server, there's a place in the configuration when you specify the port where the RPKI server is going to be listening for queries. Okay, so with this line, we copy paste it into the client. Okay, and if everything goes okay, you will have a lot of messages coming up which says, okay, connection established. Then it's going to be starting to fetch all the information, and then it's going to be disconnecting, and you should get the prompt again with everything in white, no red messages, no warnings, no anything, luckily. And now if you list the local directory content, so this is a kind of different for every Unix user, but for me, I kind of always automatically use this command to list a directory content, which is ls space minus larth. I'm not going to explain what that is. You just write that, press enter, and you're going to get a nice view of the local directory, okay? If you are used to a different way, just you do it your way, okay? So you see now, we have a new file that is just created, okay? This is in UTC, okay? So we just created this roas.csv file, which is 17 megs big. These times we should say only 70 megs. Like maybe 20 times ago, this was a huge file, but now it's nothing, okay? It's smaller than a WhatsApp picture you're sending, okay? And this file you just created should contain the whole RPKI information for the whole internet routing prefixes that already have a ROA in place, okay? Another way to say that is every single ROA that is created in every RIR for every prefix should be there in that file. And this is not a simulation. This is a real RPKI validator connected to the real internet with the real information. And to check that I'm not lying to you, we can just do a kind of search through that file for maybe for a specific information. If you go to the lab guide, you will find some ways of getting information. You see, using the command grep, you can go through the file, through a text file, and look for information. We are going to use this last one, the one that says grep and gets an ISN. And I'm gonna do this. I'm gonna put that. Okay, sorry. I'm gonna put that here. Let me clear the screen so you can have a clean view of what is going on. Okay, and what I'm going to do is any of you, can you tell me what your ASN is? 400. Sorry? 1200. Okay, 12. Is that right? Okay, that's it. That's it. Okay. So this will bring anything that has 1200 in the ASN number. If it's a longer ASN, it will also get it. But luckily, I think there's only one with that here. So you have here are all the prefixes, all the networks advertised to the internet by ASN 1200 that have a ROA in place are listed here. Okay. So this is the network, the network mask. So the network address and the network mask. This is 91.200.16.0/22 network. This 22 here is the, when you create a ROA, as was explained before lunch today, you specify the network. You basically specify the longer you admit the prefix to go. So this is an exact match because the network is a /22 and we are only admitting 22, okay? And this is the ASN that it's allowed by the ROA to advertise that prefix, okay? Any advertisement coming from any ASN for this network that is not 1200, that is not listed here, it's gonna be treated as, this is a question. So what are the three validation, exam question, what are the three validation states a prefix can be regarding RPKI? Valid, invalid, and unknown. Valid if there's a row in place for it, and if the row is correct, and if everything is correct, it's going to be valid. So all of these are the valid ones by definition. So you will only find in this file valid prefixes. Then, if a prefix is advertised, one of these prefixes is advertised either from a different ASN or with a mask that goes out of this range, for example, this first one, if it's advertised other way than /22, it will be treated as invalid. Okay? It can come from the same ASN, but if it's out of this range, it will also be treated as invalid. Okay? So the two things that made a prefix invalid are different ASN on or a network out of range, out of the range specified here. Okay? If you check, oh my God, this example you have all exact match. That is a good thing for you, but it may be other. Let's look at another one. Any other ASN number? 29909. 29909. That's it. Oh, here we have one that is not an exact match. An IPv6 prefix 2607/2800/32, and they allow to go down to 64. Okay, and that should come from ASN 29909. So if anyone advertises this network or any network out of this range, even if they are coming from the correct ASN, that will be invalid. If anyone advertises this network within this range coming from a different ASN, also invalid. Okay? And what are the unknowns? The unknowns are those that doesn't have a ROA in place yet. So if you have not created a ROA for your network, those will be treated as unknown. Nor valid, not invalid. Okay? Not invalid, nor valid. So. Good. And you can choose any ASN that you want, or you can choose any block that you want. You can browse to that file. That file should contain around, if we account for all the entries in that file should account for all of the networks that already have a ROA in place from the 5 RIRs. Okay. Keep in mind that the whole internet routing table. There's no such thing like internet routing table, but we love to call it that way. The whole internet routing table has around, like, correct me if I'm wrong, but it should be like close to 1,000 IPv4 prefixes plus maybe a million IPv4 prefixes and 500,000 IPv6, right? So it's like 1.5 million if you account for all IPv4 and IPv6. You won't find 1.5 million here. You may find less or you may find more, because there could be more information here, because if a network is allowed to be advertised by 2 different ASNs, it will be twice, right? It should be twice. You should have 2 ROAs. One that allows the network to be advertised by 29909, and the other ROA stating that this network can also be advertised by this other ASN. So you need a ROA for each ASN that you want to advertise each of your networks, okay? All right. Questions up to here, comments? Good. Not good, but anyway. Okay. So let's continue with the lab, okay? We will skip this part. This part shows, it's a description. It says verifying the configuration of the border RTR border router. This is the IXP central router that I'm controlling, that you don't have access to, and that you're going to connect to set up your BGP sessions with, okay? And this is an overview of the general configuration of the router. What is important for you to know is this router is connected to a router that is a real router in a real ISP that is connected to the real internet. This router, it's getting the full routing table from the internet, but it's filtered, so the routes that are really installed in the BGP table are not the 1.5 million routes, but a very, very, very small set of those, because we don't want to kill our virtual memory, virtual machine memory with a lot of routes. And this router already has all the BGP sessions configured with your routers. So the only thing that is pending is that you set up the BGP session on your side, and it should go up because it's already configuring and waiting for a connection request, okay? So if we go down, past this configuration, this is verifying initial configuration of DS routers of each of your groups. So now let's go into the router and let's start doing funny stuff, okay? So go back to the network diagram and click on the router. You click on your router. You click on your router. I don't know why I'm not able. So if you're not able to click on the router, just reload the page. It should work. Yeah, okay. Click on the router. This should pop up, and the prompt should say your group number, GRP X-RTR, right? So you are into the router. This is an FRR routing, CLI, very similar to Cisco CLI. So if you are used to Cisco CLI, you already know how to deal with this. If you are not used to Cisco CLI, you already know also how to deal with this. And if you never get into a router, don't worry, we will tell you exactly what you have to type, and we will explain every command before we do it. And you are going to execute it after we explain it, okay? Right. So in order to check the configuration of a Cisco-like router, sorry about that, the command, you can abbreviate the commands, etc., etc. I'm just going to tell you the short version. So if you write SH, which stands for show, okay, space, run, show run, SH space run, and you press enter, you will have the screen go up very fast, and you will be presented with the whole routing configuration, the whole router configuration, okay? This is the whole router configuration. If you go up, if you move the screen up to the beginning of the command, yeah, you will see this is the current configuration of the router. So this is how the router is running exactly now, and you will find a lot of information. We are not going through it. You have already created static routes. Don't deal with that. Don't change that. Don't add any route, and don't change the configuration of the interfaces, because this is not a simulation. You are actually accessing the router through this basic configuration. So if you change anything here and you basically cut the low where you're standing, you're going to be pushed out of the router, and you're going to be not having access for the rest of the day. So that's the end for your lab. So don't change the configuration. Go with the crowd in this time, in this lab. Okay. The router has 4 interfaces. Okay. If we look at the diagram, each router has this network connected. So this is 1 interface, 2 interface, 3 interface, 4 interfaces. Ethernet. This is Ethernet 1, Ethernet 0, 1, 2, and 3. I think. Let's check if that's correct. Yes. You have here the Ethernet 0, which connects the rack to the backbone. So this is the red network in the diagram. Then the interface Ethernet 1 that connects the router to a network we call LAN, which is the one that has the client actually. Then there's a network that we call int, like internal, and a DMZ. We use those for different types of labs. We can set up like DNS. We normally set up DNS servers in these networks, like public resolvers, or not so public resolvers. And then we set up like hidden authoritative servers, public secondaries that use XFR to copy the DNS information from the authoritative servers, et cetera, et cetera. So we use this lab also to perform DNS-related capacity building, okay? For those of you that I'm speaking a language that you do not understand, just don't worry. We are not going through that today, okay? And that's more or less everything what your router has already configured. So it's basically a very basic configuration, only with the interfaces and the IP before an IPv6 assigned to each of the interfaces. Okay, from here, the first thing you're gonna do is going further down in the guide. We are going to first. You're gonna stop here when it says. We then add some route maps and access lists that we will use later. Just stop here, and we are going to go through a brief explanation of what we are going to do next. So the next thing we are going to do is you're going to bring up your BGP sessions with the central router, okay? In order to bring up a BGP session, you will need basically BGP session relies on a TCP connection. So you have to establish a TCP connection between your router and the central router. And through that TCP connection, BGP information will flow, okay? Good. So in order to establish that link, that BGP neighborhood between your router and the central router, you will need to know the IP of the peer, the IP of the central router, etc., okay? And we have to assign our router an ASN number, and we will have to then set up the BGP IPv6 session and the BGP IPv4 session. That is what we are going to do next. Another thing that you need, this wasn't like this maybe 20 years ago, many real routers and software routers also, when you set up a BGP session, if you do not set up any policy, they will advertise everything that is on the BGP table, and they will accept everything that is advertised to them. And that's, as most of you may know, could be a huge security risk, right? It could lead to advertising stuff that you don't want to advertise, and it could lead to get networks into your network that you don't want to be there. So in this version of the router, like in most, let's say, modern router, but this has been like this for 20 or 15 years at least, if you don't have a policy in place, BGP session will go up, but it won't advertise anything, and you won't get anything from the peer until you have a policy in place. The policy could be accept all, which is the one that we are in fact going to use. So we are going to advertise all and accept all. But you have to explicitly have a policy in place that says, I want you, the router, to advertise all and receive all. If you don't say that, the router is going to do nothing. BGP is going up, and the router is going to wait for you to set the policy, okay? So you have to have the policy in place before setting up the BGP. That's the correct way of the best practice, or the correct way of probably doing it. So we are first copy-pasting this, which sets a lot of policies that we are going to be using along the lab, including this one here that says routemap todo. Sorry for putting this in Spanish. This is todo. Todo means everything, okay? So this policy, this routemap that says todo IPv4, basically it's telling the router accept everything that everybody is advertising to you, and also will send everything that the BGP has configured for advertising to other peers, okay? So this is basically accept everything and advertise everything, okay? So we first set the policy, and then we go and configure the BGP. In order to set the policies, you just copy all of this, go to the router, you cannot pass that into the router as it is. We first have to go into the configuration mode of the router, To go to the configuration mode, just write conf space T. T stands for terminal, so it's like configure terminal. You turn into the terminal in order to configure the router. That could be one of the possible explanations. If you write the command conf space T and you press enter, you will get a config between brackets, and this it's telling you that you are in configuration mode. So be careful what you do now, and you just paste what you just copied. Okay, you paste what you just copied, and you just press a couple enters. Yes. No, here there's no X in the. I guess it's no X unless I did a mistake. That's an excellent comment, but there are no X's in the policy. The policy would be the same for everyone. Okay, we'll all have the same policy. Yeah, there's no group specific configuration that you have to change, so you can just copy paste that as it is. Thanks for the question, because we will have to do it for the next commands, and if I forget, everybody's going to get errors. Thanks very much for that. In this case, everybody just copy paste this. Okay, if you do it, we can go to the router. You will have all the configuration passed, and just press a couple enters just to make sure that everything gets into the configuration, and you'll see that the configuration prompt changed. This says config route map. So we'll have to exit this section of the configuration. So you type exit one time and remain there. If you happen to type exit more than one time, you will. I'm gonna do it. You don't do this. Okay, this is something I'm gonna do. You are okay. If you are in the config part of the configuration, you are okay. I'm gonna do something just in case you do it to tell you how to go back. Okay. If I type exit again, I exit the configuration mode. So if I want to get into the configuration mode again, you have to write the conf t command again and press enter. And if you type exit again, this can happen, shit happens. You exit the router. You say, oh, I lost the lab. No, don't worry, the lab is up and running. What you have configured in the router, it's already there. You just lost the connection to the router. You just close that, go to the router, open it again. That's all, okay? Configuration is still there, all right? Okay, so we are already there. Now we are going to configure the BGP session, okay? So go back to the lab, to the guide for the lab, and now, we are going to be executing these commands one at a time for the first two commands, because we have to make changes to this, because this command will vary according to your group number, okay? So the first command we are going to execute in the router, in the configuration mode, is to tell the router we want to bring up BGP protocol, okay? And a BGP session after that. But to activate the BGP protocol in the router, we have to execute the command router, BGP, and your ASN number. This is the way we are telling the router what's our ASN, okay? And the whole router will be within that ASN, okay? In our case, we are using private ISN space from 65,000 up, okay? So I'm group 1. My ASN will be 65,001. If you are group 20, guess what? You're going to be ASN 65,020, okay? So it's 65,000 and your group, including all the zeros that you have to put in place so as to make sure that you write the correct ASN number. You can copy the command and paste it into the router and then delete the X's, and I'm going to add a 01 because I'm 55,001. But you have to replace the X with your group number, okay? If you are 20, it's 55,020, not 0020, okay? Just make sure you write the correct ASN. And then press enter. The prompt changes, and now it says config router, okay? That means that you are into the BGP configuration part of the router, okay? Next thing we are doing is we are copying the second command, which gives the router ID. What's the router ID? So in every autonomous system number regarding BGP protocol, every router needs a name, right? And every router needs a different name, a different identifier. Because every router needs a different identifier, the most common practice used is to assign the router identifier the same way as you assign an IPv4, for example, an IPv4 address. Why? Because it's easy in a network to make sure that an IPv4 address you are choosing is unique. You just choose any IPv4 address of the router's interfaces, and you will make sure that that IP will be unique, so the router ID will be unique. Is the router ID an IP? No. It looks like an IP, just to make sure that it's not repeated anywhere in the network. Okay? So we are going to execute the command BGP router ID, and we are going to use 100.64.1. And you have to replace the last X with your autonomous system number, with your group number. So if I'm group 1, I'm going to be 164.1.1. If you are group 20, you're going to be 100.64.1.20. Okay? Just copy paste the command and replace the X with your group number. 1. Okay? And then everybody's there. So raise your hand if you were not able yet to get to this point when you configure the router ID. Don't be afraid. Raise your hand because we can wait. We have time. Okay? Okay, I guess everybody's here. So let's go to the next. So the next thing you're going to do is to copy all the rest of the configuration, because the rest of the configuration is exactly the same for everybody. Why? Because the rest of the configuration, it actually brings up the BGP sessions for IPv4 and the BGP sessions for IPv6. And I told you that what you need in order to bring up the BGP session is to know the central router's IP, so your neighbor IP, and your neighbor ASN. And that's the same for everybody because there's only one central router. We are all connected to the same central router. So all the rest of the BGP configuration for this lab will be the same for everyone. So you can now copy and paste the rest as it is. Okay, make sure you are not copying the 2 first commands that you already execute. Just copy from where it says BGP log neighbor changes on. Okay, everything from there down to the end of that configuration, you copy and paste it into the router, and you press a couple of enters, so you make sure all the configuration is in place. Okay. All right. Then do exit twice, exit and exit again. So we get out of the router configuration part. And now what we are gonna do is gonna see if everything went okay, and if we have now something different, or if we are receiving, or if you are getting any route from the central router. Okay. In order to do that, we are going to be executing first this command, show BGP IPv6 unique as summary. You can copy this command. This command, what it's going to do is going to summarize all of the BGP sessions regarding IPv6, related to IPv6, that you have up and running in your router. Okay, we have one IPv6 BGP session running. There should be one IPv6 BGP session running with the central router. So we copy the command, paste it into the router, and ta-da, we have it. Okay, it should say here. It should set the neighbor, the IPv6 of the neighbor. Okay, it should mention it should appear 65000, which is the ASN for the central router. Okay, and then it says amount of messages received since the BGP is up, amount of messages sent since the BGP is up. Normally, at least for the first day, these two numbers kind of usually matches, but there's nothing wrong if any of those does not match, at least not immediately wrong. And then here, these last two that says 33 here, it's number of prefixes that you are getting from the central router. So prefix received, 33, and prefix sent, 33. Remember that we set a policy that says accept everything that somebody is sending to you, and we have a policy in place that says advertise everything that you have in your BGP table, right? And if you remember about BGP, for those of you that know about BGP, how BGP behaves, if something is if you are getting something through external BGP into your BGP table, and you have a policy that allows you to advertise everything, you are going to re-advertise that to any peer in a different ASN. So everything that you get through external BGP, you are advertising it through external BGP. Okay? So the central router is sending us, each of us, 33 routes, and we are sending back those 33 routes to the central router. The central router knows that he's the one that sent it to you, so he will discard those advertisements, but those advertisements are still there, okay? The central router is not gonna do anything with those because they come from him, but those advertisements are there, okay? Then we can execute another command in order to check for the BGP table, okay? This is a way of FRR. Recently, in the last years, this was like the original Cisco-like command to check for the BGP IPv6 route table. Show BGP IPv6 unicast. Okay, there's a very much simpler command that you can execute that is just show BGP. Nowadays, with the latest version of FRR, if you execute show BGP, you will get the IPv6 BGP table. The IPv6, not the IPv4. So FRR turning into, by default, it will show you IPv6 information, no IPv4. Why? Because that's the way it's meant to be, right? We want to go for IPv6. We are not going to do by default IPv4, because if not, we have like two phases, right? We are telling everybody, go to IPv6, and by default, everything is IPv4. No. Okay, so they turn it around, and now by default, everything is IPv6. Okay? There it goes. If you execute that command, the screen is going up very fast, and if you go up to the beginning of the command, you will have, after you execute the show BGP IPv6 unicast command, you have first here some information that is mainly a reference, like if these are all the networks. So now all the networks that live in your BGP table will be listed there. It should be 33 networks, because when we did the summary, it says that we are getting 33 networks from the central router. So here there will be 33 different networks listed in our BGP table, IPv6 BGP table. And as you may know, how to read this in BGP is first the network with the network address and the mask. This is /48. Then it will tell you what's the next hop. So what's the next network that you will be reaching, the next interface that you will be reaching if you are sending traffic towards this network. So this is the next hop. It's basically telling you how to reach this network. So for your router, for my router in this case, to reach this network, it needs to send information to this IPv6 next hop address, okay? And lastly, here is what we normally call the ASN path, which reads from right to left. So this network is originated in ASN number 12654, then goes to 161. So this is all the path, all the ASN path that this network is following from the source, from the ASN that is advertising it, up to our router. So this is basically the reverse path for the traffic. If we are sending traffic towards this network, starting from, in my case, the ISN 65001, then it will go to 65000, which is the central router ISN. Then it will go to ASN 64135, and on, up to the ASN that has this network in, okay? This is like the reverse path for if you read it from left to right, is a direct path from your router to the ASN, to the destination ASN. The most likely direct path. It doesn't have to do exactly that because something can change in the internet topology, but that's the most possible, the most feasible path that the information will flow. Okay, so always keep in mind that BGP shows you like the reverse thing, right? So BGP, the advertisements flow exactly opposite to the traffic. That's a way of simplifying the explanation. Okay. So this is the BGP table for IPv6. It's not the full IPv6 Internet BGP table because we have filtered it so not to inject 1.5 million routes in each router, because we delete all the virtual machine memory where the lab is running and we will kill in the lab. Okay, that's the why we filter the information. But these are real routes of the real Internet, because this is not again, it's not a simulation. It's a real router. Okay. But don't worry, if you make a mistake, we are not going to advertise anything to the internet because the ISP has filtered everything. Basically, it doesn't allow us to advertise anything to the internet outside of the lab, okay? Good. Next. What we are gonna do next is, now we have our router, BGP up and running for IPv4, BGP up and running for IPv6, 2 BGP sessions between our router and the central router. BGP is up and running. We are getting the networks. We are ready to go. We can now route anything from our router to any of these destinations. And because we also have a default route, we can route anything, basically anything from our router to the rest of the internet. What are we going to do next is we are going to connect our router to the RPKI server, okay, to the fourth validator, in order to get the validation information and see how our routing table, BGP routing table, not the router routing table, the BGP one, changes accordingly to that RPKI information. Remember this, before proceeding, here the BGP table shows the prefix, blah, 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 the ISP path, the ASN path, and here at the beginning, you see that there's an asterisk, right? This asterisk means that this route is valid. So that means that if you are sending traffic to this network, this is the route that is going to be used. All of the routes in the BGP table that has an asterisk at the beginning for this operating system means that, and this is almost exactly the same in every single router, all the valid routes have an asterisk at the beginning of the line in the way that the router shows the BGP table, okay? But you see that before this asterisk, there's nothing, okay? Okay. In order to connect our router to the RPKI servers, we go down here when it says finally, we must also indicate the presence of the preference of each server. So what are we going to do? We want to connect the router to the RPKI server, right? In order to connect the router to the RPKI server, we have to first activate RPKI protocol in our router. The way to activate RPKI protocol on the router is go to configuration, conf-t, then RPKI, enter. You are now have activated RPKI in the router. So now the router speaks RPKI, right? Then you have to tell the router something called at least the you should tell at least the router something called the polling period. And we are going to set 300. This is in seconds, okay? So that's 5 minutes, right? So every 5 minutes, our router will fetch from the RPKI validator the whole local repository. So the whole list, you remember when we pretend to be a router and download the full repository that has all the ASNs with all the ROAs, with all the prefixes? That's what this timer is going to tell the router how often it should get that information, okay? And again, you don't want your router to be fetching that information every 1 second. Never. Because the router has more important things to do than every 1 second getting this information from the RPKI server. So don't put that number that low, because probably you're gonna not break the router, but the router will be very busy trying to fetch all the time information from the RPKI server, and won't be very free to do what it has to do, that is route. So you normally want to put at least, 5 minutes is something reasonable. You can, again, you can tune this up to your needs, okay? If you have 100 routers connected to the RPKI server, also if you put a lower number in the frequency on the routers, much more routers will be asking the RPKI server for information, and the RPKI server will be more busy and will need more CPU and more memory to attend all the requests. So you have to play with the numbers so you reach to a good balance between how often do you query the RPKI server and how often your router gets busy doing this, okay? 5 minutes is a reasonable number. It could be more, it could be more. I shouldn't put less than 5 minutes, I mean, but that's a practical tip if you want. There may be some cases when you want to put this lower, but normally 5 minutes is okay. Again, RPKI information doesn't change that much often, so every 5 minutes is reasonable, okay? There's not a single truth about all of these timers, okay? And then we are going, of course, specify these last 2 lines that says RPKI cache and an IP address, port, and preference are the 2 RPKI servers. We saw that we have 2 RPKI servers. It's always good to have more than 1 RPKI server. Why? Because servers needs upgrades, because server fails from time to time. So you should run at least 2 different instances of RPKI server in order to get more resiliency, right? Because if you have one and you have, for example, to upgrade the operating system, you have to put it down, and every router won't be able to fetch RPKI information. If you have 2, you set a preference 1, preference 2. Guess what? The router is going to try first with the lowest preference. So first it's going to try to reach the RPKI server that has the validator, that has the lower preference, in this case preference 1. But if we shut down that server, it will automatically go and fetch the information from the server 2. Okay, so you can deal with what you ever want to do or solve in the validator that you put down, and then you put it up, and then the routers sometime later will go back and fetch information from the one that has the lower preference if they see that it goes alive again. Okay, that's automatically. You don't have to do anything. You can have 2, 3, 4, 5, as many as you want. Okay, 2 is reasonable. 3 could be. 4, you are exaggerating. Okay. And it's also another good tip here is that I'm running Fort in both of the RPKI servers. So it could be good to have one RPKI server with Fort and the other one with Routinator, for example. Why? Because software has bugs. Softwares have security issues. And if there's suddenly a huge security breach affecting Fort, you will want to put down Fort as soon as possible. But if all your RPKI servers are the same flavor, you have to put them all down, and you end up with no RPKI server. If you have 2 different ones, and something really goes wrong with one of them, you can put it down, solve it, like update the software or whatever, or wait for the vendor to solve the issue, and then bring it up again. Everything will continue with the other, because it's very, 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 very extremely unlikely that a security breach affects different software vendors, okay? It can happen. It's not impossible. Nothing is impossible, but it's very unlikely, okay? On the other side, if you want to run 2 different RPKI softwares for validators, you need to know how to run both. So now you have to learn Fort and Routinator if you want to run them. That's the kind of what it comes with running 2 different software. You have to know how to run 2 different software. Maybe you say, no, I'm standardizing everything to run only one type of software. Then you take the risk. It's okay. Okay? But my recommendation would be, it's good to run 2 different validation softwares in 2 different servers. Okay? From different vendors. All right, so we copy this and pass it into the router. First, remember to enter into the router configuration mode with conf t, and then just paste as it is. This is exactly the same for everybody. There's nothing regarding our group number here, okay? Once you've done it, just write exit once, exit twice, and in order to check if the router is correctly connected to the RPKI server, we are going to execute this command that is show RPKI cache connection. So this is basically telling the router to show you if the router is connected to any RPKI validator and a little information about that. So if we execute this command, if you execute this command and you did everything okay, it should say connected to group 1. This group 1 means the one that has the preference 1 in this case, and because this is not all the configuration that you can do for RPKI, you can define groups of RPKI servers and put all different servers with different preferences in the same group and have a second group and put some more validators there, and you can do a lot of magic with RPKI, but we are not going into that detail. Normally that is not needed, but if your network has, from certain size on, you may want to create groups and you may want to play with that. For example, you can have a group of RPKI servers that are the Fort servers. You can have a different group that are the Routinator servers, and you can have like 2 or 3 for Fort and 2 or 3 for Routinator. No, if you have a kind of worldwide network with a huge amount of routers, you don't want all the routers to cross the whole world just to reach the RPKI server, etc., etc., etc. Okay. There's also a way to secure the connection between the router and the RPKI server. We are not doing that now. We have not configured that. Everything flows in clear text. So if everyone captures the connection between the router and the RPKI server, we'll be able to read the information because we have not configured any secure protocol. There are ways to configure to secure that. But my recommendation will be always the RPKI validator interface and connection that you use to talk to your routers. It could be good if you use a management network, not not online, let's say, okay? And it could be good even to use, like, you can even use private IPs within, or the IPs that you set for your management network, which is protected by a firewall. So all the traffic between the routers and the RPKI validators flow behind a security firewall or whatever you put in place and inside your network. So it's not advisable that the connection between the router and the RPKI validator goes through the public internet, okay? Just as a security thing, okay? And there has another, and it's also, as any cache or as any server, it's advisable to have the RPKI server as close as possible to the routers. So if you have a kind of worldwide network, you may want to bring up much more validators, like close to each node when you have a lot of routers in your network. So one for this region, one for this other region, and you can create groups, and that's when groups and preferences become useful and important, okay? Anyway, we are connected to the number 1, okay? That's the summary. If you are not connected, you won't see anything here, and of course, you won't see this connected near to any of those, okay? So everything seems to be working. How can we check that? Let's execute the same command that shows us the full BGP table again, okay? That was show BGP IPv6 unicast, or show BGP, okay? And if you check now, the table will be the same with the same 33 IPv6 prefixes, but now we have a new thing before the asterisk, okay? What is this? If you go to the reference at the top, you will see it, but what is this? Anyone willing to answer that? Yeah, that's it, perfect. As all you said, this is the V stands for valid, and this is the So when the router is connected to the RPKI validator, now it adds into the BGP routing table the validation state for each prefix in the table. So if the prefix is valid, it will put a V at the beginning of the line. If it's invalid, it will put an I. And if it's not found, unknown, it will put, I don't remember if it's an N or a U. I think it's an N, like not found in the RPKI repository. Okay. Let's check. Okay. So here is the reference. For those valids, it will be V. For those invalids, it will be an I. And for those not found, will be an N. This is unknown. This is that prefix. There's not a ROA for that prefix, or at least I didn't find a ROA in the validation list from the RPKI validator. Okay. And if you check here in the table, it seems that there are all the 33 that we are allowing are valid. Okay. Anyway, we will do something now and we will see a different validation state. Okay. Questions up to this point? No? Okay. Next task we are going to do. Okay. We are going now for the next 10 or 15 minutes. So for the rest of the practical part of the lab, we are going to work with a specific IPv6 prefix and do some stuff around that prefix, okay? So first thing we are going to do is we are going to see the BGP status, the ASN path, and the validation state for a specific prefix, okay? If you go to the lab script, let's say, we are going to be using this prefix, right? The IPv6 prefix 2803.9910.0000-48. Okay, that's a prefix. If you do a RDAP query or a whois query, you will get that's a prefix that's allocated to LACNOG. Okay, it's really allocated to me because of LACNIC's policies. They cannot allocate something to an organization that's basically not exist, because by that time LACNOG has wasn't established as an independent organization. Now it can be assigned to LACNOG, but anyway, this is a prefix I requested. We at LACNOG requested as applying to a specific policy that LACNIC has, that you can apply for research and capacity building IPv6 space and ASNs. So we requested an ASN, an IPv6 block, and they give it for free if it's for capacity building and research, and you have to make an annual report on that. And if you use that for anything but capacity building or research without any profit from it, they just take it away from you. Yes, it has to be for that, and it's going to be free as long as you use it exactly for that. Okay, I don't know if Erin has a similar policy in place, but yeah, we get it from LACNIC because they have that policy, and we knew them, and we could apply for that. Okay, so, but this is not a private space. This is public space. So we copy that command, the show RPKI prefix and that specific prefix into the router and execute it, right? And if you see, I execute the command show RPKI prefix blah 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 /48, and it says prefix is this, and this is this prefix belongs to this network. The network that it's really advertised to the internet is not a /48, it's a /34. Okay, and we allow that prefix. There's a ROA in place that states that prefix would be allowed to be originated in ASN 64135. That's one of the LACNOG ASNs, and we allowed to be subnet into down to /48. So from anything coming from ASN 64135 regarding this network from /34 to /48, it's okay, will be valid, and anything that falls out of this window or originated in a different ASNs will be invalid, okay? This prefix cannot become unknown because there's a ROA created. And unknown is only for those that don't have yet a ROA, okay? Good. And if you see, the state is valid because it is showing here that it's falls within this range, okay? And if you check in the routing table as we did before, this prefix, this network, the /34, this is the network we are looking at for the 48, but this is the network that is being that we are getting from the internet, comes from ASN 64135, which is the correct one, and it's within the allowed mask, so it has a valid state. Okay, so now we know the network. It's in our BGP table, and its RPKI state is valid. Okay, if this network becomes invalid, nothing is going to happen. Nothing is going to happen because this is very important. When you connect the router to the RPKI server, you're not changing anything, any behavior in terms of filtering networks or affecting networks. You're just seeing new information and interesting information and useful information, which is the validation state. But the router is not going to do anything by default with that information. If you want to see it, you just have to list the BGP table. But there's nothing that the router is going to do, even if this becomes invalid or unknown or whatever. Okay? That's important because some people say, oh, but if I activate RPKI and connect the router to a RPKI validator, that means that if a prefix becomes invalid, I'm going to filter it out so I can start having routing issues. No, nothing is going to happen. Okay? Nothing is going to happen until you set a policy using the RPKI information. If you set a policy using the RPKI information, of course, something is going to happen, but you did it on purpose. Okay? So up to this point, it's only useful information. You can see it. The router is doing nothing with that. Okay. Let's now get a more specific prefix and see what's going on with that prefix in the BGP table. So if you go down in the lab guide, when it says analysis of a particular prefix as a demonstration, we are going to use the same prefix 2803.9910.0000.1. So only one IPv6 address from all the /34, okay? And we are gonna, the first command we are gonna execute is show BGP IPv6 unicast with that prefix. So we are gonna check for the BGP table only for that prefix, okay? We go to the router, we execute the command, show BGP IPv6 unicast. So the same command to list the whole table, but we only add this prefix at the end of the command. And this IPv6 address, the router is telling us, okay, this IPv6 address belongs to a /34 network, okay? It has all, this is the ASN path, so this is originated from, so this network, the /34, is originated on 64135 ASN, then jumps into the 65000, which is the ASN of the central router, and then it goes into my router, which is 65001, but it's never going to be listed in the ASN path. So the ASN path in the routing table never shows your own ASN, okay? Or at least not in this CLI. If I would have done this, I would have shown, but that's me, not the ones that invented this, okay? But there's a reason it's not shown, okay? And then here it says RPKI validation state valid. So this is a valid prefix, okay? Good. Let's follow the lab guide. So now let's go back to the network diagram and open the client again. Probably if you left the client open, because we took a lot of time since then, it must be closed. So you close the window and go to the diagram, network diagram, and open the client again. So we are back in the client, okay? And if you see the lab guide, what we are going to execute is this command in the client. This is not in the router, it's in the client. MTR and the IPv6 address we are playing with, okay? MTR, it's basically an advanced, pretty way of doing a trace route. It gives basically the same information of a series of trace route, only it keeps refreshing, and it's kind of a real time showing what's happening with the route. The information follows through the internet from your client to the destination address. Okay, so if you execute this command in the client, sorry, wrong command, I didn't copy. Have to copy first. It's not gonna work. MTR and the IPv6 address in the client. You will see this, and you will see this updating in real time. So it shows all the hops, all the networks that the information is crossing through along the internet towards the destination address, which is the address you are doing we are doing the MTR to, or we are doing the trace route to. Okay, and it shows each of those hops with the percentage of packet loss, the minimum and the maximum latency, etc., to each of those steps. So it's more or less the same as a series of trace routes will show you. Only it's in real time, and you don't have to touch anything, and you will see how things change in the routing path through the internet. And at the end, you see that says no route to host. This means that this prefix is not really assigned to any host. So this IPv6 address we are tracing is not really allocated to any device, to any host, or that there's a firewall in front of that network that hosts that host that it's filtering this kind of ICMP trace route type of packet, okay? Anyway, there's nothing wrong about this. It's only that there's no allocated to any device. We are going to left that up and running, okay? And now I'm going to perform an attack, okay? Just allow me a couple seconds, okay? You can manually refresh the MTR by pressing the R letter, but anyway, it's gonna refresh automatically, okay? But if you wanna give it a try, just press R a couple times so as to force a refreshment of that. Nothing should be changing there, okay? Just allow me to I'm going to stop sharing for a second or two. Okay. Just refresh, press refresh. What happened? I'm not sharing the screen. Sorry. But you tell me, what are you noticing? So trace has changed, right? So the route, the path through the internet to that destination address has dramatically changed, right? Now it's only 3 hops, and now it seems to be someone with that address allocated because you can reach the destination. So what do you think may have happened? What type of attack is this? How we call this kind of? So now the information towards that IP address was going to some place in the internet, and now it's going to a completely different place. through a complete different path. There's an attack that has to do with BGP that has a name for this, and that's hijack. That's a prefix, hijack. So someone, somewhere, it's telling the internet from a router with a BGP session, they have the prefix now. They have that network. They are advertising that network from a different place, okay? That is one possible explanation for this. Let's check. So we go to the router, okay? We go to the router, back to the router. You can use the up arrow to execute again the show BGP IPv6 unicast, the same command that we executed the last time, and check for what is happening here, right? If you execute the same command, now we see, first of all, what's this? Is there anything different here? You see anything different here? Now it's a /48. So now this IPv6 suddenly is not from the /32, but /48 network. Okay, so someone is advertising a new network that wasn't there 5 minutes ago. And if you check for the RPKI validation state, it's invalid. Why it's invalid? Because it fall out of the window, of the mask window? No. Why is invalid? That's it. Because the ASN that it's originating this prefix, if you look at the ASN path, it's not the one that ended up in 135. Now it's the 65002. Oh, it's someone that has group number 2 that is doing the hijacking. So I have the group number 1 and number 2, and from the router of my group number 2, I triggered an attack. So I advertised it through BGP to the central router, the same this more specific network from the ASN 65002, which is not allowed by the ROA to be the origin for that network. Okay? So the network range is okay, but the origin is wrong. Okay, so RPKI state changed it. Are your routers doing anything about that? No. That's the reason when you refresh the trace, the information is going to a different place. So you're not filtering, you're not doing anything with the RPKI information, but you can see that something is wrong here now. So the sole thing of bringing up an RPKI validator, connecting the router to the RPKI validator without doing anything else, gives you a very useful tool for operations to debug this kind of attacks. Another, because this can be on purpose, someone really willing to steal your traffic, or by mistake. You know, the very well known several years ago misconfiguration from Pakistan Telecom that made a famous Google allocated prefix to be routed to their network, and that had a lot of side effects. First effect is their network was dead because they killed the network, because a lot of traffic that was supposed to do, I don't remember if it was like something from Google, from YouTube or whatever, all the traffic started going to the network, and the network hasn't got that bandwidth, so they automatically get run out of bandwidth, and for all those accessing those services from Google, they weren't able to access the service because the traffic was going somewhere else, and it took some minutes or some hours to solve the issue and for the internet to propagate the solution and for the traffic to start flowing the correct way. And by that time, the RPKI didn't exist, so they weren't able to, by doing this kind of the kind of thing we are going to do, using RPKI to set a policy to solve the issue. So this is something that can happen on purpose, by accident, by misconfiguration, someone typing faster than thinking, etc. Okay? If you work in a network operations center, raise your hand if you never made a mistake. And if you raise your hand, I'm going to be telling you a liar. Okay, I'm going to tell you a story. When I was as I normally say in previous life, I used to work for over 10 years in a network operation center in my country, in Uruguay. The major operation center from Uruguay. We had a border router that was in the other side of the city. We didn't have offline management network running that day. You know, shit happens in the correct timing, never when everything is in place. We were doing maintenance of the management network. The network was offline. There was no way of putting that online in a day, and I was configuring a router, and it was a Cisco router, former Cisco router. Like this was 20 years ago, or more than 20 years ago, like 25 years ago, and I just have a new set of policies in place, an access list, and I just pasted the access list into the router. So you know how Cisco routers used to work, like first line, you put, when you paste the configuration, first line, as soon as the lines are written, they take effect, right? And the first line just basically cut me off the router and cut everything. So the router got completely disconnected from the backbone. Of course, the rest of the configuration never made its way in, and the router was left out of the backbone of the network. No management network. Router 25 minutes away in a taxi, and that was a border router with something like 20 gigabits of traffic towards the country. So basically, we say, oh, you know the word, right? And I say, okay, what do we do? And like 5 minutes of everyone blocked, and they say, okay, bring a taxi, call a taxi. And we jump into a taxi, we went to the data center, and we basically took the fiber optics that connect the router to the international links and do this. And then the router stopped advertising because there was no router connected, and then the traffic started to flow through the correct path, okay? But because basically we created a black hole in the border of our network. And that happens. Yeah, it was a mistake from someone that was starting. No, I wasn't starting. It was a mistake from someone that has a little experience, but even though we make mistakes, okay? Can you blame the one that made a mistake? Yes, you can, but it's not useful at all, because nobody should blame someone in operations because of that kind of mistakes. Probably our biggest mistake was that we didn't have enough procedures in place. If you have enough procedures in place, like things written down, and you follow them, it's more difficult to make those mistakes. Okay? If you had an alternative management network, you won't have that issue. You can make the mistake, but you can solve it in 5 seconds, right? Etc., etc., etc. But even though, shit happens, always. It's not when, it's not if it's going to happen, it's when it's going to happen. Sooner or later, it's going to happen. You have plenty of examples of huge operators, well-known, that have more difficult issues to solve than this one, right? And of course, after you know what it is, it's very easy to solve. How can they have come to done that? Yeah, but shit happens, okay? Everything is easy to solve after it's solved, okay? Then, how we solve this? Okay, what we're gonna do is we're going to set a policy based. We are gonna use our RPKI information, and we are gonna use that. We know that this is invalid, to try to get rid of that prefix and see if by removing that prefix from the BGP table, we can restore the traffic to the real destination, okay? And so you keep running the MTR in the client, and I'm going to show you the BGP table, again, the full BGP table with show BGP. If you want, go to your router and do show BGP, and you will see here that we have 2 prefixes now for the same, two networks for that prefix. The /34, which is valid, which is the original one, and that is coming from ASN 64135, which is the correct one. And then we have this one, which is the the hijacked one, that is a same network address, only more specific, okay? With invalid states coming from 65002, which is the ASN that is hijacking the prefix, okay? And we should be able to get rid of this, to remove this entry, the invalid one, from the routing table. If we succeed in removing this one, our router is going to use this one, which is the correct one, and the traffic should be restored, right? How do you do that? Well, in order to do that, and following the lab guide, we have here, we have to first enter the configuration file on the router. So please do conf t in your routers, okay? Once you've entered the configuration file, you have to enter the BGP process. Remember your ASN number, and you write router, BGP, and your autonomous system number. In my case, as I'm group 1, is 65001, okay? You have to get into your BGP process. Then you have to get into the part of the configuration that relates to IPv6, because we are dealing with IPv6 prefixes. In order to do that, you can copy-paste the command from the lab guide, but the command is address-family space IPv6 space unicast. Okay, so address family IPv6 unicast into the router. Okay, like that. Okay, so it's router BGP, your autonomous system number, then address family like this, IPv6 unicast. We are configuring the BGP regarding IPv6, and then you can copy paste this from the live guide. I'm going to put it here so you can see it, and I'm going to explain it. This says neighbor, and it has the IPv6 address of the central router. So this is going to apply to the BGP session between our router and the central router, which is the one that we have up and running for IPv6. And it says route map RPKI in. And if you go back and look at the policies we copy-pasted at the beginning, that we said we are going to be using that along the lab, the RPKI policy, basically, I'm going to show it to you here in the lab guide. I'm going back to the very beginning of our lab, when we copy-paste all the policies here. Here. Remember when it says we then add some route maps and access lists that we will be used later. And if you look here, it says route map RPKI permit 10 and route map RPKI permit 20. The first policy in place for this policy called RPKI. So I called the policy RPKI, and I say match RPKI valid. What this means is this policy will match all the prefixes in the BGP table that have valid RPKI state. Okay? That's what match RPKI valid means. And then I'm going to do this. So this is the matching sentence, and then you have the action. Once this policy matches the valid prefix, it will change the local preference of those prefixes and put it to 200. Okay? The default local what's the local preference? The local preference is one of the first things that the BGP algorithm will check in those cases when you have two BGP routes, exactly the same routes, and you have to choose between those two, because you cannot choose the more specific because they are exactly the same, but you have two paths with different routes. There's a sequence of tests that the BGP protocol will go through in order to choose one of those. So you want to first see what has the major local preference, the higher local preference, and it's going to choose that. If they have the same local preference, it's going to, let's see what has the shortest ASN path, and it will choose the shortest path. Then if the paths are the same, it will go through a lot of stuff until the end is almost like throwing a coin, right? And choosing if everything is exactly the same from the two of them, it will, even in that case, it will select one of those. It will be because choosing the one that has the lowest IP number in X interface, or the router that has a lower router ID. There are a lot of ways to resolve that difference, okay? And if everything is okay, and if everything is exactly the same, you have an option also to configure something called BGP multipath, which cuts the resolution process at some point in order to have both networks in the routing table. That's not the case. We are not going to get into detail about that. The router is always gonna, as it is configured now, the router is always gonna choose one path to each network. If it has two paths for the same network, it's gonna choose one of those. One of the first things that it's gonna use for taking that decision is the local preference. Local preference, default local preference is 100 normally. We put it higher, 200. So what does it mean is this policy here means that if for every valid prefix in the BGP table, for every valid prefix, those prefixes will be put with local preference 200. We have priority over exact equal prefixes with lower local preference, okay? And there's another entry in the policy that says match RPKI not found. So for those prefixes not found, those are going to be left with local preference 100, which is the default local preference in this case, okay? So if they are not found, they are gonna have local preference 100. If they are found, they are gonna, if they are valid, they are gonna be with local preference 200. And what happens to any policy you set, if there's a policy for something that matches some of the case, any case that fall out of this policy will be rejected. So if we apply this policy, valid prefixes, local preference 200. Not found, local preference 100. And what happens to unknown? Unknown prefixes will not end up installed in the BGP table. So basically you are not allowing invalid prefix to be installed in your BGP routing table. That means that there won't be a path in the BGP routing table for invalid prefixes. Now, if we apply this, we are taking an action in the router. So the router will remove from the BGP table all of the invalid prefixes, okay? But only when we apply this. We didn't yet apply it. We have the policy in place, but we didn't apply it. Now what we're gonna do is we are going to apply the policy. In order to apply the policy, what we're gonna do is we are gonna copy this command, the neighbor blah, blah, blah. I'm gonna put it here in the router to make it easy for you, okay? So the command is neighbor, the IPv6 address of the neighbor, fda11.c858.10, routemap RPKI in. This in at the end means that I'm applying this for incoming BGP advertisement. So every information about BGP prefixes that my router is getting from the central router is going to be filtered out of invalid prefixes, okay? Good. I apply that, exit again, and exit again, 3 times, okay? So I return to the normal command line for the router. And we are going to do now, we are going to execute the same command that we executed before, like see what's going on with that prefix that we want to solve the hijacking, right? And if we check now, if you were able to apply all those, you will see that the prefix is now back to the correct network /34, and it's back into valid state. And if we check the whole BGP table with show BGP command, you will see that the invalid prefix disappeared from the BGP table. Why? Because we just applied a policy that says get rid of all of the invalid prefixes from the BGP table, okay? Now, were you able to do this? Go back to the client and press R, refresh. What happens? Oh, we screw up the log. No, everything we do is correct, and this is correct. We haven't solved the attack. Why? The? Who may be missing RPKI? The? Sorry? It's the border router, the central router. So this is the thing. We did put a filter in place for each of our routers. So in our BGP table, everything is okay. Now our router is sending the traffic to the correct next hop, right? But what's the next hop for us? The central router, right? And the central router takes its own decisions. It doesn't care if I'm running RPKI, whatever. The central router is a different network, in a different ASN, with their own policies, their own decisions. The central router apparently has not RPKI in place, so they keep having their wrong path in the table. So this is an important thing. For RPKI to work, all of the ASNs, all of the networks in the path to the destination need to have RPKI in place. Because if only one of these networks doesn't have RPKI in place, you won't solve the issue, okay? Because we are running out of time, we'll cut the lab here, but the following step is only one step remaining. I should go to the central router, apply the same policy, and you should press the R, and the traffic should be restored, okay? And you will have to trust me that is what is going to happen. What I'm going to do, if you want to give it a try in the following days, I'm gonna leave the lab up and running, you keep the access, you have the lab guide, I'm gonna put that command in the central router so you can make sure that the central router will have RPKI in place, so you can putting and removing the RPKI or changing the policies or whatever you want, okay? So this is the end of the lab. I hope that it gives you, at least an experience for those of you that never configure BGP or never played with RPKI, to have a first-hand try of what this involves. You see that it's not difficult. You see that even if you configure all the RPKI and you have the information in your router, nothing is going to happen, nothing is going to change in your router until you apply a specific policy, okay? So next step that I would recommend anyone and everyone here, because sooner or later you will have to deploy RPKI, is you can go set up an RPKI server, connect your routers to the RPKI validator, and start getting this information, the validation state in your BGP tables. If you do only that, if you do not apply any policy, it's okay. You will have one more tool to debug issues, which is knowing if a prefix is valid, invalid, or not found. And that's a lot of information for those of you in operations, okay? If you want to go further and feel confident enough to apply a filter, you have all the right to do that or not, okay? But the fact of getting that information into the router is very useful for operations, okay? Just as a final words, to link this with DNS, what we should do, and we can leave that for a future event or a more longer time for you to play with this. We have now a router with RPKI configured in our ISP, right? We can set up, for example, 2 DNS servers, whether they are authoritative servers or recursive servers, and we can set up Anycast, right? So Anycast, it's a way of having redundancy for any service that has. I think one of the main important things is that if you have 2 servers in an Anycast configuration, both servers have to provide the same service, and both servers need to have the exact same information. As long as that is true, your Anycast will work properly. Because if you have Anycast and you have one server with different information than the other, depends on what server your clients and what information they get, okay? Because Anycast is basically assigning the same public IP address to 2 different servers, okay? And how to configure Anycast in a DNS server? Well, there are many ways. One of the easiest one is to run an FRR router in each DNS server. So you have your router, the one that you already configured, you have 2 DNS servers, both of them with an FRR instance running on them. And you set up an internal protocol like OSPF between the FRR servers in the DNS servers and the central router. And you advertise from both of them the Anycast prefix. If you do that, you can develop a very easy script that when the DNS server goes down, the FRR server, the FRR router that is running on the same DNS server stops advertising the Anycast prefix. If the server stops advertising the Anycast prefix to the central router, then you have no route to reach that DNS server, and the DNS traffic automatically flows to the other. When you restore the server, this starts advertising the Anycast prefix again, and the traffics begin to balance again. In order to balance traffic using OSPF, you have to configure your OSPF session to have something called equal cost multiple path, ECMP, and you have to put at least 2 or 3 or 4, depending on how many servers you have. So your router, the router that you just configured, can put in its routing table more than one route for the same prefix. Okay. Once you've done that, you are up and running with Anycast for DNS or for whatever service that you have, and you can use that either for authoritative servers or for recursive servers. And you can. The other thing that you have to bear in mind is that DNS uses UDP by default, but if the information is too much for a UDP datagram, you will use TCP. And if you are load balancing traffic using TCP, you can get into troubles because first packet is sending here, second packet send here, but you have a TCP connection. So all packets should go to the same place regarding the same connection. In order to do that, the load balancing algorithm for OSPF that you have to use, that luckily is the default one, is to balance traffic, not doing a round robin, but to use flows. That's the default behavior of OSPF balancing algorithm, so you are okay, but you have to know that. When you are doing TCP and balancing stuff with TCP, you have to keep the connection. So if you do a round robin, you basically screw up the balancing algorithm, okay? So you always use per flow balancing, not per packet balancing when you're balancing something that uses TCP as the protocol of connecting, okay? Questions, comments? We all want to go, right? Enough for today. Okay, thanks very much, and see you next time.